Here's the classic ladder problem. Imagine this is a ladder leaning against the house, and this wall has no friction. We'll have friction down here. As the ladder moves away from the wall, we're going to reach a point where we can't go any further without having the ladder fall down. Is there some way that we can relate the angle to the coefficient of static friction? Let's find out. So here we have the wall and the floor. Here's the ladder. We'll have no friction on the wall, and we'll assume all the friction is on the floor. We have the length of the ladder and an angle at the point at which this ladder will start to slide out. We have the weight of the ladder and the normal force from the floor. That's the only force that can hold up this ladder because the wall produces no friction. And there's a normal force coming from the wall. What's going to stop that normal force from pushing the ladder and sliding it to the right? The force of friction holding it to the left. And if we've pulled the ladder as far from the wall as we can without having it fall, then we've reached the maximum static friction. Since we have two normal forces, we'll distinguish them by labeling them 1 and 2. We know that the ladder isn't moving, so that means the sum of the forces has to be 0. That means the weight is going to be stopped by the normal force from the floor, and the normal force from the wall will be stopped by the friction coming backwards. But we also know that the ladder isn't rotating, so we'll say the sum of the torques is 0. We'll try choosing the bottom end of the ladder as the pivot. Torque counterclockwise equals torque clockwise. The weight of the ladder is making this rotate counterclockwise. But what's the distance? It's going to be 1/2 the distance from the wall to the pivot. And this distance could be found by taking L times cosine theta. So we need 1/2 of L cosine theta. What's going to stop that torque? The normal force of the wall making the ladder rotate clockwise. And what's the distance for that force? It's going to be the height where the ladder contacts the wall. And again, that can be found using trigonometry. And there we have our two torques. Notice what happens to L. They cancel. And you may recall that Fn2 is also equal to the force of friction static maximum at this moment. Well, we're getting closer because we want to get the mu s in there. Yeah, mu s times Fn is the force of friction static maximum. And do you know what Fn is? That's this Fn. And that's equal to Fw. So what happens to the Fw? Now the weight cancels too. Can you see what mu s equals? 1/2 tan theta. Now that's not any theta. That's the angle at which we reach the point where we start to slip out and break static friction. Let's measure that angle. It's starting to go. It's somewhere right about here. I'll measure the angle with the meter stick. I have about 22 centimeters on the X and about 46.5 centimeters on the Y. So that's 46.5 for the Y, 22 for the X. All we have to do now, plug in the values. Well, I have a mu of about 0.24. Now, how do I know if that's reasonable or not? Remember when we said the wall was frictionless? That's not a bad assumption considering that there's not a lot of normal force pressing against here. It's mostly down here, and that's where we're going to say most of the friction comes from. So we could just lay this board flat on the floor here and measure the force of friction that it takes to start it moving. I pull ever so slowly and see when it starts to jump. I get about 2.3 newtons. And now I need to know what this thing weighs. I don't have the right spring scale, so what the heck? I'll just weigh half of it, just see how much it takes to lift one end. I get about 6 newtons, and that means the weight of this thing is about 12. And so here we have the board laying flat on the table. I pulled forward until I reached the maximum static friction. And we just measured the spring scale to be 2.3 newtons to get it started. The weight was 12 newtons. And taking the force of friction static maximum divided by the normal force, we get 0.19. Okay, not the greatest, but not too bad. We're in the ballpark. This seems reasonable. Now you might say, hold on, wait a second, that's not really fair because the friction is coming from just this edge, and then we measured the coefficient of friction with the whole surface in contact. Is that really comparable? Well, remember we had this problem when we studied friction, What would happen if you reduce the area? Well, you might say less area would give you less friction, but remember, there's more normal force per each square centimeter in contact. When I increase the area, I have a lot of area, but I'm going to have a lot less force on each square centimeter. And the two variables cancel out. Well, that's about the hardest torque problem we've seen because it also involves friction. There's all sorts of variations on the ladder problem. For example, we could have a massless ladder of length L leaning against the wall with a distance to the bottom of the ladder, given a mu s. How far up the ladder could, say, a painter climb before having the ladder slip out? I'll let you worry about that. Don't fall.